So this is the last big theorem of vector calculus, which is the divergence theorem. So before we get to divergence theorem itself, let's first take stock of all of the different integral results that we have seen. So they are written on this first page. Um, And you can kind of go through them and check that, yeah, we've talked about all of these, right? So, I mean, obviously, this is all the way back in Calc 1. This one, fundamental theorem of line integrals, relates taking the integral over a gradient vector field, right? A gradient vector field like this. And so, since you have a gradient vector field, that means that the vector field is conservative, which means that you don't need to integrate along the curve. You can just evaluate at the endpoints of the curve, which is there. Um, and then we have two different versions of Green's theorem. One which corresponds to a line integral, right? A vector line integral. One which corresponds to this flux form of the line integral, where you end up dotting with n. And when you do that, well, this over here is like taking curl of the vector field and then only taking the z component of it. So that's why we were dotting it with the vector k. And then over here, this guy looks a lot like Divergence, except the two-dimensional version of it, because we don't have a r sub z in the integrand. And then lastly, we had just learned about Stokes' theorem, so that is connecting a line integral like this with the well, the only difference between Stokes and Green's theorem is that with Green's theorem, it assumes that your two-dimensional domain D was a flat region, typically on the xy plane, whereas with Stokes' theorem, the two-dimensional integral is over a surface whose boundary is C, and you'll see that as we have we're relating this two-dimensional integral of this measuring the flux over this other vector field, curl of f, and it's relating it to a circulation integral along the boundary of your domain S, which is called C. And in these paragraphs, I'm also noticing I'm kind of setting up all of these integrals in the same. I'm ordering them in the same way, like the left column and the right column all are kind of corresponding with each other. So notice that on the left column we have essentially one more integral. Think of this as like there not being any integrals, perhaps. So on the left column we have one more integral, but we have a derivative in the integrand. If you think about the gradient as a type or a derivative, yeah, the gradient as a derivative. This is the curl. If you think about the curl as a derivative, if you think about the divergence as a derivative, then it's like these integrals on the left-hand side all have a derivative operation being done to the argument in the integral. So in a sense, it's like it's simplifying the integrand, right? So we end up having one more integral. So the integral itself, or the region we're integrating over, is more complicated, but the integrand, the thing we integrate, is simpler due to the taking of the derivative. Also, the note that the right-hand sides are all they all kind of should do this as well. So the the right-hand sides all have one less integral. So it's like the region that you integrate over is simpler. These are like integrals in 0 dimensions. They're just evaluations at points. These are line integrals. Fine. In contrast with the two-dimensional integrals. But the function that you integrate over is, well, more complicated in the sense that it's no longer the derivative version of the thing. Instead, it is the thing itself, right? So you don't have derivatives on the right-hand side. Okay. So I'm bringing this up primarily because on the exam, you need to be able to recite basically Green's theorem and Stokes' theorem, and if you want to do the extra credit, the divergence theorem as well. You're not given these theorems on your formula sheet, although you are given the formulas for computing things like line integrals and surface integrals, the definitions involving the parameterization, but you're not given Green's theorem, Stokes' theorem, divergence theorem. So you have to be able to recall them, which the difficulty lies in getting kind of the structure of the formula correct. So I would think of it as there being a trade-off in the difficulty, right? Either you are either you're the thing you're integrating is like the integrand is simpler, meaning that you took a derivative of it, but the integral that you're performing, the thing you're integrating over, like the region that you sweep your integral over, that would be more complicated. Or you have the reverse situation. The region you're integrating over is simpler, but the function is more complicated. In a sense, I can actually, and you'll see also, so let's just kind of bring up divergence theorem, and then I'm going to write something in a second. But yeah, divergence theorem also follows in a really similar way, but instead of comparing an integral in 2 dimensions with an integral in 1 dimension, it jumps up a level. It goes ahead and does an integral in 3 dimensions and an integral in 2 dimensions. And you can see that the pattern is still there. I wrote it in the same order, right? So this has one more integral, but the integrand is simpler because we took a derivative, versus over here, it's that the thing you integrate over is slightly easier. Perhaps slightly easier. It's easier in the sense that there's one less dimension to it. Let's put it that way. But the integrand is slightly harder, perhaps. And yeah, just to make sure that it makes sense what the divergence theorem is saying. So this triple integral is over the solid. So, for example, I guess in this picture here, well, okay, so this almost looks like a rectangular prism, except it's kind of puffed out. But the triple integral would be over the volume. So every point in this cuboid-like shape, and that would be how you would compute the right-hand side, right? All the points in 3-dimensional space that are inside this region that confusingly has not been labeled the correct thing. See, it says it's supposed to be labeled E, but this is labeled V, so I don't know. Maybe I'll say it's also the same as E. Okay, and that's the left side. The right side is the surface integral. So this thing looks like it has 6 different sides. It looks like it has 6 different boundary components. Oh, gosh, 6 different boundary components. So if you were to compute it through this right-hand side, you would actually need to parameterize all 6 boundaries and then compute the surface integrals of them and add them all up. So this divergence theorem is saying that the two are equal. One additional comment I need to make, right, about how about the assumptions involved with divergence theorem. So orientation does matter for this. So it requires that the orientation of the surface of the region, so the boundary of the region, right? All of these, the surfaces that comprise the boundary of the region, E, all should have counterclockwise orientation. Or, counterclockwise. Well, no, it's better to call it outwards orientation. But when you look at each of these faces, it will look like counterclockwise orientation because of the right-hand rule. There's kind of an example where we can see that with parameterizing it. But you can see that in this figure, all of the normal vectors are pointed outwards from the volume, from the solid, right? This face down here is pointed downwards. This face in front of us is pointed towards us. This face that's supposed to be in the back, right? It's pointed back, and you see left, right, and up. So all of these normal vectors are pointed outward from the solid, and that's the correct orientation for divergence theorem. That makes it so that the signs all match up, and that makes this equality happen. Okay, now what I was going to say, coming back to, where's my cursor? Coming back to relating all of this with, well, I guess the rest of the theorems. So, I just want to make a comment that, so you're not going to fully understand what this means, but Stokes' theorem actually generalizes a lot further with higher level math. Well, maybe not a lot, but it does generalize a bit further. So instead, it's one way to write it. If I keep the same order, it'd be like, um, oh gosh, the only right letter is omega, isn't it? D. All right. Well, I've already started to do that, so that's unfortunate. Is it right to do it this way? Let me think. Something is not quite right in how this is being expressed. Okay. Yeah, so this is probably not exactly what you find, but this is like this is Stokes' theorem in general. And so we already said that Green's theorem is like Stokes. Also, you can kind of see that the flux form of Green's theorem is like divergence, since the flux form of Green's theorem, which is right here. Okay, why is the flux form of Green's theorem, which is right here? It has something very similar to divergence inside. So if you bring that up a dimension, notice that you end up getting this. Right? We bring it up a dimension, and then we introduce an integral to both sides. So this does become that. And I guess I should probably say a little bit more about what this is doing. So on the left-hand side, we have one more integral in the sense that we're integrating over, or wait, okay, I did that. I think I did it the other way around. Whoops. df integrate with respect to it's actually, yeah, the problem is it's not written this way. It's not written this way, unfortunately. So it's more like it's more like written in this format, where omega is a differential form. So it ends up having these differential elements that you would make sense of, but then this guy is the exterior derivative. So then you are taking a derivative of this this form. But effectively, what's happening is that there's a trade-off in the d. So you see that here on the left-hand side we have d happening inside of the integral, which is similar to this kind of situation where the argument you're integrating, there's a derivative being taken on it. On the other side, the d, instead of being in what you're integrating over, it's showing up in the set that you're integrating over. So instead of M, which stands for manifold, it's the space that you're integrating over. Instead, on the other side, we simplify by taking the boundary of our set, which brings the dimension of our integral down by 1. So you can see that Stokes' theorem satisfies this, Green's theorem, and divergence theorem. They all, I think actually every single integral on this page basically can be thought of in this way. Yeah. Right, so those are all the main points that I wanted to hit, I think. Okay. Yeah, all right, so I had just said that. So divergence theorem is like Green's theorem, the Flux version of Green's theorem, but in one higher dimension. I had pointed that out just now, right? Looking at this formula versus looking at this formula, you can see um, you can see how that's the case. All right, let's now start doing some examples involving divergence theorem. So, all right, we're given this vector field, and we're given a surface S that consists of a cone, described like this, z from 0 to 1, and with a circular top. Okay, so yeah, the solid itself, if I think about the solid, I'm thinking about a solid cone, which then has two different pieces to it. It has a circular top, and it has this lateral side to it. S itself, the way it's being described, it sounds like S is supposed to be both parts. Okay, we assume that the surface is positively oriented, which should mean that the normal vector is pointed outwards. Okay, and I believe there's an illustration. Good. Okay, so this problem wants us to verify divergence theorem. So we're going to compute both sides of a divergence theorem for this problem. So first, we start with computing the triple integral side. So we do a triple integral over this. This will be a scalar function. Once we take the divergence of a vector field, we get a scalar function back out. We can quickly check that for this vector field, the divergence is equal to 2. So we take the x derivative of the first function, giving us 1, the y derivative of the second function, giving us 0, the z derivative of the third function, which gives us another 1. So divergence ends up being the sum of all of that. So 1 plus 0 plus 1, which is going to be 2. So we do get that the divergence of f is 2. Okay. So then this triple integral is going to simplify, right? Since 2 is just the function inside, this triple integral now, you can pretend there's a 1 there. This is measuring the volume of the region E, right? The solid cone. So, well, we know the formula, or at least I would hope that we know the formula for the volume of the cone. So for all pyramids, it's 1/3 of base times height, basically. Going from cylinder to pyramid, you take 1/3. So yeah, so 1/3 base times height. Base is clearly going to be the so the circle of, in this case, it's unit. Its radius. Oh gosh, its radius 1, I believe, is just given to you in the setup. Although I didn't quite point that out. So it's because z goes up to 1, so then when you insert that into here, you see that the uppermost part of this region has x squared plus y squared equals 1. So it's a circle of radius 1 at the top, which is how we know that this circular face is going to be radius 1. So plugging into the formula for volume of a cone, it's 1/3 base, which is pi r squared, times height, which is 1. And so all of that together gives you this as the triple integral. Okay. Now for the more tricky part, the surface integral of this region. So this surface is comprised of two different parts, right? You've got two piecewise smooth, I think is the phrase. So you have two parts that are piecewise smooth. You have this circular part, and then you have this lateral side. Right? They glue together in a non-smooth way, but that's fine because we only need piecewise smooth. So I'm saying here that S1 is going to be labeled for the top, and S2 is going to be for this lateral surface. Okay, we need to compute both of them and add them together. So starting with computing the surface integral, computing the flux across S1, well, we need to parameterize S1. So that's a disk, right? It's a disk sitting on the plane z equals 1. So we can parameterize it using basically polar coordinates. Well, we then tack on the z coordinate, so maybe you can think of this as cylindrical. So u ends up being my radius, and then v is my theta, basically. So we end up getting this parameterization for the surface S1, the circle on top. You compute, in order to compute the surface integral, we end up needing to compute this guy, right? So once you plug in the parameterization to this vector surface integral, you'll have to, well, you directly plug in the parameterization here, and then you fix any of the, I guess, region distortion by using Tu cross Tv. Or at least that's the aspect that takes the normal component of the vector field. You're dotting of this to get the normal component of the vector field. Okay. So we have to compute those parts, which is why we end up computing the tangent vectors and taking their cross product. I believe that process is pretty straightforward. We also have to plug in the parameterization. So f was something slightly complicated. It was like x minus y and x plus z and z minus y. So you can check it that by inserting this parameterization into the vector field f, you do get this guy right here. And then lastly, we want to take the dot product of these two, and thankfully this normal vector is going to select only this last function. So we end up getting this. This is what we integrate over the surface S1, which, well, okay, once we've inserted the parameterization, that's actually going to a different space, right? This integral is happening in the xyz space. But once we've inserted the parameterization, then the function inside is taking in arguments u and v. So this integral is happening in the uv space, where you have u going from 0 to 1, v going from 0 to 2 pi, which is convenient because, well, that's a rectangular domain in uv space, right? Although in xyz space, that's actually a circle, right? So we have a change of coordinates happening there. All right. And, well, we calculated what this was up here, so we insert that in. And then what I'm stating here with this cancellation is that this latter term goes to 0 if you take the integral, which should be clear if you think about it, right? So imagine that you're doing this double integral just over this term. Well, it's a function of u and v separately. So you could split it off into a product of two one-dimensional integrals, and then you end up having this integral from 0 to 2 pi of sine of v dv. That's going to go to 0, which is why the whole thing goes to 0. Right. That only leaves you with the integral, well, of this term, of u. If we only consider that, then we can easily collapse the integral with respect to v. That's going to just be 2 pi, which is why we end up with a 2 pi there. And then we integrate that, u going from 0 to 1, u squared over 2, evaluate from 0 to 1, the over 2 is going to cancel with 2, so you just end with pi. Right. So that is the flux across the circular top S1. As described there. We also have this other part of the boundary of the cone, which is this lateral surface, S2, which we also need to compute. So we need a different parameterization, which I've called R2. And, well, this definitely uses cylindrical. So, well, these two arguments are the same, right? So u again is acting like radius, v is acting like theta, and we end up having u as our z component function, and I think that's just to make it match this. So this equation says that r squared equals z squared. If you take the square root of both sides, you get r equals z. So another way of, yes, around here. Yeah, another way to sort of visualize this is that you have r here, you have z here. This is supposed to be a cone. So you end up getting this kind of shape. And, well, it's actually supposed to be 1 and 1. This is supposed to be a line, r equals z. Where did that just go? This is the line. Z equals r. And r is going to be x squared plus y squared. So when you square both of and then you take the square root. So when you square both of these, you take the square root. You end up just getting u. Okay, so you can also see that from there. Okay, we're still computing. We're trying to compute the same kind of surface integral. So a lot of the steps are, or a lot of the partial calculations are going to be the same. We compute the tangent vectors, compute their cross product. So notice that it's a bit more bothersome in this case because the normal vector is not just isolating one component, it actually has multiple parts to it. And then also I'm being picky about orientation here because orientation does matter in this instance. So if you look at this, the vector given from this calculation, this is actually inward pointing. So the way you could see that, so think about this picture, but bring it up to like 3 dimensions, or it doesn't really matter if you think about it in 3 dimensions or not. Like take the x component and take the z component. So this is saying that in terms of x, or in terms of r, the way that this is labeled, it's pointed in the negative direction, so to the left. But for the z, it's pointed up. So if you take just like a point here that's on it, I'll use a different color. If you just take a point that's on this lateral surface S, what this tu cross tv is saying is that that vector ends up pointed this way, which is inward. It's pointing into the solid cone. And so that is not the right direction. You want all of the surface integral. You want all of the surface that is part of the boundary of the solid. You want all of that oriented outward, with normal vector pointed outward. So what we do is we flip these two, or we just introduce a negative into all of this, so that we're using the correct normal vector. Okay, so we just end up negating all that. And that's why this guy turns into this, where I've switched u and v here. It's to use the correct normal vector. Yeah. So inserting, that's what I'm doing here. Inserting the parameterization into f, inserting r2. Again, it's a little bothersome. It's, what was it, like x minus y, y minus z, something. You can check it out on your own to see that I am actually matching it up. X minus y, x plus z, z minus y. Okay. So it is, if you insert that into the vector field f, you'll get this. And then you dot this with the normal vector, which I've tried to spell out all the steps for actually doing the calculation. It's a little bit bothersome, but not too bad. I'm just trying to confirm it mentally. It's a bit. So we take u cosine v, dot it with both of those. You end up getting a u squared that you can pull out. Sine squared and then sine cosine. Okay, and then u times sine v multiplied by both these terms. You can factor a u squared out from that product. You then have cosine v sine v, and you also have sine v. Okay, and then this last guy is, you can again pull out a u squared from. If you do that, you get 1 minus sine v. Yes. Okay, so yes, that is the dot product of these two things. Then we can simplify that a little bit, which will certainly be necessary because we have to integrate over this. Pull out the u squared, you get all of those coming from, yeah, all the things in parentheses. And then there's a slight cancellation. So you get this minus sine v cosine v and plus sine v cosine v. And I think that's, oh yeah, and the sine v's doubled up. So here we have this. So that is as simple as we can get the integrand for our surface integral. We now compute the flux across S2. We compute the vector surface integral. Okay. All right, which will become that. And again, the bounds are coming from the parameterization. So the left-hand side is technically in XYZ space. Once we've inserted the parameterization, we've flattened things out. Our double integral is now over this flat region in UV space with whatever it was. So U running, no, over here. U running from 0 to 1, V running from 0 to 2 pi, which you can see the variables are matching up here, right? So U running from 0 to 1, the outer integral, V running from 0 to 2 pi, the inner integral. And we just have inserted the integrand that we computed above. That got inserted here. And, well, this, you can see, is a product of two functions, a function of U and a function of V. So we can split this double integral into a product of one-dimensional integrals. So this integral is straightforward. This one, yeah, so having done integral from 0 to 2 pi of sine squared and cosine squared enough times, I know right away that's pi. This is going to go to 0 because this integral is capturing a full period of sine of v. And then this is going to be minus 1 times the length, so 2 pi. So we got that. And so this whole thing computes to minus pi over 3. Okay. So we computed the surface integrals over both S1 and S2, both parts of the boundary of the cone. Then we have to add the two results to get the total surface integral, or the surface integral over the entire boundary S, which the book is also calling the total flux across S. So, well, the first guy we had computed was pi. The second was we computed was negative pi over 3. So we end up with 2 pi over 3. And you can check that, if we just scroll up a little bit, that matches with what we computed on the left-hand side of divergence theorem with this triple integral. We computed also that we got 2 pi over 3. So we were able to, from all of this calculation, we were able to verify divergence theorem for this one example. Okay, so hopefully you can understand how this works now. So we have, I think, one, maybe two more examples. So divergence theorem, again. Yeah, this is just saying when it can come into play, right? So, so sometimes it's basically if the boundary, if doing the surface integral is difficult, but doing the volume integral is easy, that's one way that you could use divergence theorem, is to do the integral over the solid. The other thing is that, well, perhaps the vector field you're trying to integrate over is difficult, but if you take the divergence of it, it turns out simple, then that will make you want to use divergence theorem in the other direction. So usually there's something that will simplify things. Okay. In this example, okay, so we are talking about a cylinder. Z going from 0 to 2, it's going to include the top and the bottom, and it involves this vector field. So if we were to compute this directly, if we were computing the surface integral directly, well, the cylinder comprises of 3 parts. It comprises of the circular top and bottom, and also the lateral side to the cylinder. So that would involve computing 3 separate surface integrals and adding the results. It's doable, but it's going to be tedious. Well, I mean, in the abstract sense, it's doable. I actually don't know for sure that it's doable given this vector field. But potentially it's doable. But if you instead, the point is, if we instead do the divergence theorem, well, all three of these pieces of the cylinder would be the boundary of the solid version of the cylinder. So we could do a triple integral over this the solid cylinder, right? R running from 0 to 1, theta running from 0 to 2 pi, z running from 0 to 1. And then our triple integral would involve us taking the divergence of this, which is probably the next step that I have written here. Okay, so apparently I didn't even bother to slow it down. So let's just think through this divergence of this. So x derivative of the first function ends up being x squared. X derivative or y derivative of the second function is going to give you a y squared. Z derivative of the third function is 1. So we get x squared plus y squared plus 1 as our divergence, which is right there. Yeah. And yes, Stokes' theorem is saying this. So we were told to compute the surface integral, but by divergence theorem we can instead compute this volume integral. And then this is setting it up so that everything is in cylindrical coordinates. So notice that we convert the integrand over, so x squared plus y squared equals r squared. And then since we're going from this, which in a sense is in Cartesian, we then convert over, we end up introducing the Jacobian, which is this r here. And then setting up everything that we need for cylindrical, well, z goes from 0 to 2, r goes from 0 to 1, theta goes from 0 to 2 pi, which is, yeah, that goes through every point in the solid cylinder. Okay, so we can proceed to integrate this. Let's see how I did this. So theta, this integral is independent of theta and z. Well, the function inside is independent of theta and z. So you can pull out those integrals. Or you can think of this as like splitting this triple integral into a product of 3 one-dimensional integrals. The theta integral is just going to contribute a 2 pi, and the z integral is going to compute a 2. Contribute a 2. So altogether, those two give you a 4 pi, and then you're left with the integral of this from 0 to 1, which is right there. And that's easy enough to integrate. That's a polynomial. So you can go ahead and do that, and you end up with 3 pi. Right. Yeah, so here's another example. We have that there's a velocity vector field given like that, and C is supposed to be the solid cube, and S is the boundary of this cube. So that is unfortunate naming, because that is kind of the other way around from how we're used to thinking about it. So for some reason, the book has just decided to use C for the cube and then S for S for the boundary, which I guess makes more sense because we've been using S for surface. The problem is that we've been using C for other reasons. So it's not ideal that the book does this. But yeah, so this is the solid cube, x going from 1 to 4, y from 2 to 5, z from 1 to 4. And you're supposed to compute the flow rate of the fluid across S. So flow rate of fluid, that is talking about the flux integral. So it's asking you to compute this double integral of the velocity vector field across all 6 sides of the cube, which is what I've mentioned down here. Right, so computing the flow rate of the fluid across S would require this surface integral, which would technically require 6 different pieces, 6 different flux integrals, one for each face of the cube. So instead, we use divergence theorem. And that actually really simplifies things a lot because of how this vector field works. This vector field is particularly nice. So notice that if we take divergence, x derivative of the first guy, that's 0. Y derivative of the second guy, that's also 0. And z derivative of the third guy is 0. So this taking the divergence of this vector field, the integrand ends up just being 0, so you're doing a triple integral of the function 0, and that's just 0. You don't even need to actually integrate over the cube in this case. So yeah, that's the end of the notes, but I'll just try to elaborate a little bit more on this because the book kind of does, and I didn't write it down. The book goes on to say that if your vector field is of this form, some function of y and z, f, g, so then some function of x and not y, x and z, and h, some function of x and y. Right, the purpose of doing this is that the divergence, and I guess I can put an arrow there, the divergence of f is going to equal 0. Okay, so vector fields that are kind of nice like this, they simplify drastically, and so much so that you don't even need to compute an integral after you've applied divergence theorem. I wouldn't say that that's a very common thing to happen, but it is something you can at least look out for, that sometimes taking divergence of the vector field drastically simplifies your vector field, and so is worth the trade-off of introducing an extra integral, right? That's the whole point of all of these theorems that we have. We're doing trade-offs between what's more difficult. Either we're integrating a more difficult function, or we're integrating over a region with a higher dimension. And you want to use the side of the theorem where the computation is easier. So there can be certain trade-offs. Okay. I guess that's all I have to say about that. Where's my cursor?